math, right? But on the other hand, it's not good because then everything is subjective. Is it homogeneous? Is it heterogeneous? Depends on whether it has bubbles in it or not, right? With numbers, you're right or you're wrong. Yes, maybe you can get a little off the path on your way and get partial credit, but there's a right or a wrong answer. Okay? It's not, I think it's wrong, you think it's right type of thing. Today, it's all math. It's all math. Okay? Some of it's going to be easy. Some of it's going to be hair-pullingly aggravating. Okay? And unfortunately, it is just the rules of chemistry. Some of these things, this is just how it goes. Anyone who's ever taken chemistry has learned these things. Everyone who's taken chemistry has questioned why they're learning these things. And to be honest, some of them, even once you get into chemistry, you still don't use. But the rules of chemistry, when you take chemistry to begin with, you have to learn them because in some situations they are relevant. Okay. So today we're going to talk about measurements, and then we'll get into our math and our numbers. Okay. So I put this up here as an example of why units matter. Okay. This was 1999. NASA sent an orbiter to Mars. It crashed, or either crashed or missed Mars, I don't remember, because one team used centimeters, one used inches. And I didn't realize the other one had used the other unit, so the parts didn't fit together, and they completely missed Mars. They didn't get it. Okay? So units matter. You have to have units. Every numerical answer that you give in this class has to have a unit. Okay? Whether it's centimeters or grams or kilometers, anything. Okay? Don't say what is the mass of a can of Red Bull, and you say 8. 8 what? Okay? All of our measurements, we have something called SI units. Okay? This is an international system that these are the main units for those measurements. Okay? Some of them you're familiar with, some of them you may not be. Remember, in science, we use the metric system. Okay? So, length, the SI unit is meter. Okay? Not feet, not yards, not miles, meters. Okay? Mass is kilogram, not pounds. Volume is liters, time is seconds, temperature is kelvins. Okay? You're probably familiar with meters, kilograms, liters, and seconds. You may not be familiar with kelvins unless you've taken chemistry or physics. Okay? It's not Celsius, it's not Fahrenheit, it's kelvins. And we'll talk more about this. And then the last one, the hardest one to wrap your mind around, is the number of particles. The SI unit for that is called a mole. Okay? So we won't talk about the mole today. A mole will have a whole lecture later on, and then you'll use it the entire rest of the semester. With metric system, you may know we take these SI units and we have different prefixes on them. Okay? You know there's meter, and there's millimeter, and centimeter, and kilometer, right? All those prefixes have a power of 10 associated with them, and then there's also a symbol. Okay? So at this line here, we're at a meter. Okay? Anything below this, these units are smaller than a meter. Anything above that line are things that are bigger than a meter. Okay? These are the most common ones. There are ones that fall in between these, but they don't get used, so they're not up. Okay? So a centimeter. Does anyone know or remember how many centimeters are in a meter? 100. Okay? And if you are expressing 100 in a power of 10, how would you express that? 10 to the 10. Okay? 10 squared is 100. So centimeters, we say that it's 10 to the negative 2, okay? Because 1 centimeter is 1/100th of a meter. If we wanted to convert something from centimeters to meters, we would divide by 100. If we have 50 centimeters, and if you divide by 100, we get 0.5. 50 centimeters is half of a meter. Okay? If you want to multiply, you would multiply your 50 times 10 to the negative 2. That's the same thing. Mathematically, that's the same. So the prefix centi means times 10 to the negative 2. Milli means 1/1000th, which is 10 to the negative 3rd. In some cases in this class we'll use micrometer, that's 10 to the negative 6. We won't go below that. Okay? You don't need to be too concerned about nanometers and picometers. You're going to consistently use centimeters and millimeters. 1 or 2 times you may run into micrometers. Going the other way, how many meters are in a kilometer? 1,000. Okay? 10 to the 3rd. So 1 kilometer means meters times 10 to the 3rd. Okay? So if I wanted to convert kilometers to meters, I would take the number of kilometers, multiply it by 10 to the 3rd. Okay? So if I have 1 kilometer and I multiply it by 10 to the 3rd, what do I get? Number of meters, and what is that number? 1,000. Okay. They all work exactly the same. Some of these numbers they're bigger or very small, so it's harder to do in your head and visualize. But there's mega and giga. You'll never see mega and giga. Okay. Kilometer, kilo is very common. Okay. So really the only ones you have to be concerned about are kilo, centi, milli, and possibly micro. Okay. And I think we'll do some examples on how to use these. These are the SI prefixes for mass. If I go back and forth, what's different between them? I don't know why this computer's so slow. Does anybody see any difference in the prefixes? Right. At the end here, we go from grams for mass. Here we have meters for length. The prefixes stay the same. If you have centi, that applies to any SI unit. You can put that in front of anything. Centiliter, you could have a centimole if you wanted to. So, I think last week we talked about matter as anything that has mass, right? But we didn't really give a definition for what is mass. Mass tells you how much matter you have. Okay? And the way we measure that is on a balance. Okay? Mass is similar to weight. Here on Earth, in our type of lab, we use mass and weight almost interchangeably. Okay? But they are slightly different. Weight is influenced by gravity. Say I weigh 150 pounds, I wish. But if say I weighed 150 pounds on Earth, and I go to the moon, I'm not going to weigh 150 pounds because there's less gravity on the moon. Okay? But if I measure my mass here, mass is consistent. Mass does not change with gravity. So say I weigh 150 kilograms on Earth, I'm going to be 150 kilograms on the moon also. Okay? Remember, the SI unit for mass is grams. In our lab, we'll basically be doing everything in grams. Okay? Like I said, we measure mass on a balance, and we'll do this. I think it's the 3rd lab. So we'll use all of these balances and do a whole bunch of measurements. To give you an idea of different scales of masses, one salt crystal, one of those tiny little salt crystals, weighs about 50 milligrams. Remember, a milligram is 1/1000th of a gram. So a salt crystal weighs about 50 thousandths of a gram. That's not very much, right? A person weighs about 70 kilograms. How many grams are in a kilogram? 1,000. So a person weighs 70 kilograms. How many grams? I said weight. If a person has a mass of 70 kilograms, what is their mass in grams? 70,000 grams. You can interchangeably go between units, and they're all correct. 70 kilograms is just as correct as 70,000 grams. Another thing we measure is volume. Volume is how much space something takes up. You probably calculated the volume of different shapes in your math classes, right? So what is the equation for the volume of that type of shape? Length times width times height, right? When we're dealing with solids, we usually report their volumes in the unit cubic centimeters, okay? In medicine, a lot of times they talk about cc's. Give the patient 50 cc's of saline, something like that. A cc is a cubic centimeter. Both those words start with c's, right? That's a cc. So, if we measure this, we measure the volume of this cube, okay? We don't have length and width. All we have is height. How can we calculate the volume of that? Right, it's a cube, so the length and the width are the same as the height. So it's 2 times 2 times 2, right? Which is 8. 8 what? Cubic centimeters or centimeters cubed. They both mean the same thing, just how you say it. If we're dealing with volumes of liquids, we normally use milliliters, okay? And actually, it's very convenient. The way the liters line up with cubic centimeters, 1 cubic centimeter is exactly equal to 1 milliliter, okay? So 1 cubic centimeter equals 1 cc equals 1 milliliter, okay? It's just with solids, we use cubic centimeters. With liquids, we use milliliters, okay? You would be completely correct of saying if I had a bottle of water, giving me the volume of that water in cubic centimeters. It wouldn't be normal, but it would be correct, okay? And you could give me the volume of this pointer in milliliters. It wouldn't be normal, but it would be correct. Okay? How many milliliters are in a liter? 1,000. So if you wanted to convert 2 liters into milliliters, what math would you do? In this case, you would multiply by 10 to the third. So I always have to do it in my head. I think, if I'm going from liters to milliliters, is my number going to get bigger or smaller?
Smaller.
Bigger.
Yeah.
Bigger. It's like going from miles to feet. If I go 1 mile, I went a whole bunch of feet, right? If I'm going from liters to milliliters, my number's going to get bigger. So do I multiply by 10 to the third or 10 to the negative third?
Negative
10 to the third. If I multiply by 10 to the third, my number gets bigger. If I multiply by 10 to the negative third, it gets smaller. The other way to look at it is, do I multiply by 1,000 or do I divide by 1,000? Which one is going to make my number get bigger? Multiply. That one may be easier for you to remember and figure out as you're doing it. If I multiply by 1,000, I'm going to get bigger. I'm going to divide by 1,000, I'm going to get smaller. Which one do I need to do based on, do I want to get smaller or larger? Okay. So, I want to convert 25 milliliters to leaders? Somebody walk me through.
U times 2,000 by 1,000, right? Or you want me to tell you by the way that you're keeping them?
However you want to do it. And thank you for raising your hand. We don't, not going to need the, if I'm talking or someone else is talking, go ahead and raise your hand. If I'm just asking, go ahead and say it, okay? So I have 25.0 milliliters. What do I do with that to convert that to liters?
Times that by 10 to the negative third.
Times 10 to the negative third. And why are you times 10 to the negative third?
Because going from a small unit of measure to a large unit of measure.
Right. So if I go from milliliters to liters, my number is going to get smaller. Okay? So I'm going to multiply by 10 to the negative third, which gives me what? 0.25. Okay? So there we're using the times 10 to the power. Okay? If I wanted to do the multiply or divide method, how would I do it here? For this same problem. Right. So I could go 25.0 milliliters divided by 1,000 equals 0.025 liters. Okay. So here's a little more complicated one. We want to convert 25.0 milliliters to quarts. And it just tells you that 1 liter equals 1.057 quarts. Okay. Before we start, looking at that, what is bigger, a liter or a quart? Actually, it's the other way around. It takes 1.057 quarts to equal 1 liter. So the liter is bigger. Okay? You can always think of an example. First one that comes to my mind, if I say 1 yard equals 3 feet, which one is, you know which one's bigger, right? A yard is bigger than a foot. It takes 3 feet to equal 1 yard. Okay? So you need to look at that and see it takes 1.057 quarts equal 1 liter. A liter is bigger. Okay? So if we want to convert 25.0 milliliters to quarts, how do you want to do that? Convert it to...
Convert the milliliters to liters first.
Yes, yes. Because we're not given a straight conversion from milliliters to quarts, right? We know how to convert from milliliters to liters, and then it tells us how to convert from liters to quarts, okay? So I want to convert 25.0 milliliters to liters. How do I do that?
Divide by 1,000.
Divided by 1,000, okay? And that equals 0.025 liters, okay? So now I have 0.025 liters. How do I convert that to quarts? Right. So you have to think, if I'm going from liters to quarts, is my number going to get bigger or smaller? Right. Your number is going to get bigger because quarts are smaller. So it takes more of them to get to where you were. Okay? So if I want my number to get bigger, do I multiply or divide by 1.057? Multiply. 1.057. And does anybody have a calculator to do that, or do I have the answers on the slide?
Yes,
Yes,
0.026.
0.02.
I have
Okay.
3 in my calculator.
Okay.
264.
Which makes sense, right? Because a liter and a quart, they're very, very similar, right? But a quart is just a little bit smaller. It takes just a little bit more your number is just a little bit bigger. Okay? That's always a good check when you get to the end. See if it makes sense.
Now, the units would be quarts when you're done, right?
Correct.
Okay.
There we have quarts.
You have liters and slide.
Yes, that right there should be quart, QT. Thank you. So, when we get later on today, we're going to talk about a method for doing conversions called dimensional analysis, and that's going to actually help you do some of these. Okay. At this point, they're simple enough that you can do them mathematically, thinking it through. Later on, it'll get more complicated, and dimensional analysis is going to help you. Okay. We talked about mass and volume. Another thing we can calculate is density. Okay. And density is mass divided by volume. What that tells you is how much mass you have for every amount of volume that you have. Okay? If you know the mass of an object, and you know the volume of an object, you can calculate the density, right? So if D equals M over V, I'm sure that equation's on the slide coming up. It's mass divided by volume, okay, equals density. You can do algebra here, right? There are three variables. If you have any two, you can solve for the other one, okay? So these types of problems are really, really common. They may give you the mass and the volume, calculate the density. They may give you the density and the mass, calculate the volume. They may give you the volume and density, calculate the mass. Okay? You can rearrange that any way you want, okay? If we're dealing with solids and liquids, we normally give our densities in grams per milliliter or grams per cubic centimeter. That's generally a useful unit. If we're dealing with gases, gases are big. We normally use grams per liter. Okay? Gases have very low density, so we need a liter, a large amount, in order to get a number in grams that's way up. Okay? So, solids and liquids, grams per milliliter, grams per cubic centimeter. Gases, grams per liter. But like with your other things, if you give me a correct number with any unit, it is correct. It's not normal, but it's correct. So you can give me the density of a solid in grams per liter. This is just densities of some common things. You can see they really vary, right? Helium and oxygen are gases. They have very low density in grams per milliliter, which is why we report them in grams per liter, so that we don't have these tiny little numbers. Water, by definition, has a density of 1 gram per milliliter. That is where the scale was set on purpose. And if you mix oil and water, does the oil float or sink? It floats. Oil has a slightly lower density. Higher density things go to the bottom. Okay? If you put a piece of gold in water, is it going to sink or float?
Sink.
You know it sinks, right? Well, maybe you've never dropped gold in water, but you can imagine that gold in water would sink, right? It has a high density, 19.3 compared to 1, so gold sinks. Okay? Solids have high. One exception, and we'll talk about this later on, is ice. Ice is a solid, but actually has a lower density than liquid water, which is why ice floats. You know ice floats. Maybe you thought of that was weird, maybe you haven't. But it actually is weird in the terms of science. There are very few solids that are actually less dense than their liquid. So here is this equation, density equals mass over volume. Here's our cube again. If the mass of this cube is 11.2 grams, what is its density? How do I calculate this?
11.2 divided by 8.
So I have 11.2 grams divided by 8 what?
Centimeters cubed.
Cubic centimeters. Equals. Do I have it on the slide? If not, someone calculate it.
1.4
grams
grams.
per.
1.44 grams per cubic centimeter. Okay.
Oh,
You can get that unit a couple of ways. One, you can know if we're dealing with a solid, it's grams per cubic centimeter. But also we have grams divided by cubic centimeters. Okay? So here we have grams divided by cubic centimeters. Okay. So, we'll do this in lab. I don't remember when, but we'll do this in lab. These are a bunch of liquids in a graduated cylinder. Which one of these is the most dense? One on the bottom. Which one's the least dense? One on the top. Okay. Here's a person in the Dead Sea. What is more dense, the person or the Dead Sea? The Dead Sea. This works just like that. There's two things. The one that's more dense goes to the bottom. Okay. We tend to think of the person floating, but in reality, they're just finding where they want to be. The Dead Sea wants to be on the bottom. The person wants to be on the top of the water, right? What if that person was not in the Dead Sea? What if that person was in Lake Alice? They'd probably sink. The Dead Sea is very, very dense because of all the salt that's in it. It's much more dense than even the ocean. If you ever swim in the ocean, you probably know it's easier to float in the ocean than it is freshwater. And the Dead Sea is almost impossible to sink. So if you can't swim and you want to swim, is that Israel or Jordan? Is it Israel? You can go to Israel and then you can swim without fear of drowning. Just keep your head above the water. Okay. The cube of gold in this picture is a greater mass than that of the aluminum cube. Which one has the greater density? And now I will tell you, this is sort of an optical illusion. These two cubes are the same size. Okay? To me, when I look at that, it looks like the gold one is bigger. I don't know if you see that also. But they are actually the same size. So, the same size, gold is greater mass than the aluminum. Which one is a higher density?
Gold.
Gold. Why?
Same size cube, that's greater density.
Right. If you have the same volume, when you increase your mass, your density is going to go up.
Say that again?
If we calculate density with this equation, in between the two, the volume is the same,
Okay.
right? So in the gold, this M is larger.
Okay.
With a larger M, we get a larger D. Okay? Conceptually, you can think of it this way. Density is how much mass you have per volume. Here, volume is the same, but the gold has more mass in it. So even if you didn't want to look at it through an equation, you can figure it out. The gold has more mass per volume, so it's more dense. Assuming these two, the gold foil and the aluminum foil, have the same mass, which one has the greater density?
Gold.
Why?
The lower volume.
Right. So, in this case, our M is staying the same. The larger our volume is, the lower our density goes. Does everyone see how that works? They're inversely related. As the volume goes up, density goes down. Okay? So gold has a small number here, aluminum has a large number here.
Could you repeat that? You said the lower?
The lower the volume, the higher the density. They go in, density and volume go in opposite directions, because volume is on the bottom of this fraction. Okay? As this volume goes up, you divide by a larger and larger number, so your density goes down. Does that make sense? Do you want to talk about it? So, here are a regular Coca-Cola and a Diet Coke floating in water. Has anyone ever seen this?
No.
Sugar.
Coca-Cola actually sinks and Diet Coke floats. Why do you think that is? What about the sugar?
Sugar's more dense than.
Whatever the sugar jack.
Right, so in regular Coke, you have water and sugar. And when you mix those two, what you get is more dense than the water that you started with, okay? Diet Coke is mostly water with a little bit of artificial sweetener in it. Artificial sweetener is very strong. You don't need very much of it. So you put just a little bit of solid in the Diet Coke and a lot of solid or corn syrup in the Coca-Cola, so this gets more dense. Why is Diet Coke floating though? If it's water and it's in water, why is it floating? When we have a solid, we have a metal can.
Carbon dioxide is in solution.
Right. There's also carbon dioxide in there, which lowers the density. And there's also probably at the top a very small bubble. Okay? And that's enough to make it float. It's not going to float very fast, but if you let it sit there, it will slowly come to the surface. So if you're ever trying to get regular Coke out of a cooler of melted ice water, reach to the bottom. The Diet Coke's at the top, regular Coke's at the bottom. So let's go back to ice. Why does ice float? If this is a solid, that's a liquid, that's a gas, you can clearly see that the density is going down because the volume is going up, right? So why does ice float? Anyone know?
Volume actually increases when it freezes, when water freezes.
Right. Go.
Crystalline structure.
Exactly. Water is unique. Say you start with 4 water molecules and they're very compact like that. When they form a solid, they form a very spread out crystal structure. We'll talk more about crystal structure, but we'll say when you form the crystal structure, you're now like that, those 4. So they actually spread apart a bit. That's not
But they're still kind of close together, connected.
right. So if we had liquid water, maybe we would have something like that. Okay. No, I'm sorry. That's not right. Because liquid water is more dense than ice, which is why ice floats. So liquid water may be something like that. Okay. So it's more dense than the ice. Most solids won't expand like this when they form. So here we see it. Here's liquid water, and there's the ice. See, it forms this really uniform pattern, right? But now we have this empty space in here. When you get empty space, your density goes down because you get spread out. Another thing we measure is temperature. You're very familiar with measuring temperature, but probably in Fahrenheit, some of you may be Celsius. Probably not Kelvin. So temperature is a measure of how hot or cold something is compared to a standard. Okay? And that standard is going to be different on the different scales. You measure temperature with a thermometer. You know that. There really is no better way to do it than a thermometer. In science, we use Celsius and kelvins. We do not use Fahrenheit. There will never be a problem in here where the answer is in Fahrenheit unless it's a question asking you to convert from Celsius to Fahrenheit or something like that. These are some conversion formulas, okay? And from here on out, you'll be given a handout for the quizzes, the same handout that you'll have for the final exam. These are on there. So you don't have to memorize these, okay? These will come in handy if you memorize them, because eventually when we start talking about gases, you'll use it continuously, okay? But that's very easy. To convert from Celsius to Kelvin, you add 273.15. To convert from Kelvin to Celsius, you subtract 273.15. Fahrenheit and Celsius going back and forth is a lot more complicated, but you don't have to memorize that. These are our three temperatures, and they all have different reference points. Okay? Celsius is the one we use the most. Its numbers actually make the most sense. The freezing point of water in Celsius is 0. The boiling point of water in Celsius is 100. Our room temperature is around 22 to 25, depending on where you set the thermostat. You know, probably know, ice melts, water freezes in Fahrenheit at 32. You may know water boils in Fahrenheit at 212. Okay? Kelvin has these weird numbers in what we would consider normal ranges. Ice melts at 273, water boils at 373. Those numbers don't make sense. Where does this come from? It's actually because, has anyone ever heard of absolute zero? Absolute zero is 0 kelvins. That means it's the complete lack of heat. Okay? We'll talk about this later on. Temperature is actually measuring how fast molecules are moving. At absolute zero, molecules completely stop moving. Okay? No one has ever achieved absolute zero. We can get very, 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 very close to absolute zero, and people can't really even agree what would happen if we actually did achieve absolute zero. Whether nothing would happen or if the world would end. There's no way to know unless we do it.
Let's not try.
Another thing we talked about with measurements is precision versus accuracy. And this one is going to be a little tricky. If you were starting from scratch, it wouldn't be. But unfortunately, people use these terms all the time in a non-scientific way. And in science, they have strict definitions, which don't necessarily match with the way people use them when you read the newspaper or online articles or books or anything like that. Okay? Precision looks at how repeatable a measurement is. Okay? If you take 5 measurements, how close are they to each other? It doesn't matter whether they're close to the actual number. Okay? I am 5'11" tall. Okay? If you measured me 5 times, and the first time you said I was 3 foot, second time you said I was 3'1", and so on, right around 3 foot, your measurements would be very precise. You're certainly not accurate. You're way off. But what we would say that you're precise. Accuracy is how close the measurements are to the actual value. And what actually matters here is the average of those measurements. If you take 2 measurements of my height, and you say I am 6 foot, and then you say I am 9 foot, the average of that is what? 6 foot, 9 foot. 7'5". That's not very accurate, right? What if you took 2 measurements and you said I was 3 foot and 9 foot? What's the average of that? 6 foot, which is very close to 5'11". So even though neither of your measurements by themselves are anywhere near my actual height, the average is very close to my actual height, So you would say your measurements are accurate. That seems strange, but it's true. So here's a target that we were shooting. Would you say that that is precise?
No.
No. They're spread way apart, right? Would you say that's accurate?
No.
No. You have to kind of visually figure out where's the average of those. Now, I would say the average of those is sort of maybe here. It's not in the bullseye, right? Now, so that's not accurate and it's not precise. Is that precise?
That's
Yes.
precise.
The very tight grouping, but is it accurate? No. How about this one? Accurate and precise. Okay, and how about that one? Accurate but not precise. So they're spread out, but the average of those is pretty close to the center. Let's do some more conversions. Okay? You're going to do a lot of these. We want to convert 12.0 grams to milligrams. How do we do this? 12 times 1,000. So we have 12.0 grams times 1,000 equals what?
12,000 milligrams.
$12,000. Okay. What if I want to convert 12 grams to ounces? How do I do that? Let's look at this. It says 1 ounce equals 28.34 grams. If I go from grams to ounces, is my number going to get larger or smaller?
Ounces are 1 milligram.
It's going to get smaller. Okay. This is saying that it takes 28.34 grams to weigh the same amount as 1 ounce. Okay? So you need more grams to equal your ounces. So if you go from grams to ounces, you're not going to need as many ounces, right? Your number is going to get smaller. So how can we use this to go from 12 grams to ounces?
By the 12 grams by 28.3.
Right. 12.0 grams divided by 28.34 equals, is the answer up there?
0.42342.
423, we'll leave it there. So you could think, if I multiply by 28.34, my number is going to get bigger, which is the opposite of what we said was supposed to happen. We said it was supposed to get smaller, which means I need to divide by 28.34.
Are you aware that this page is covered up by red?
That one?
Yep.
Yeah, it just.
I normally delete those so that you can see the slide. Does anyone need more time to copy that? Everybody good?
Significant figure.
Sig figs are significant figures. So this rat, I would guess, spent a whole bunch of time writing a lab report, did everything right, had all the right answers, submitted it, got it back, and he lost points because he didn't use sig figs. Okay? This is going to be you all semester. Okay? We don't have lab reports, but you're going to be doing math the rest of the semester, and you always have to use sig figs. If you don't, I will mark it wrong. Okay? Sig figs are this thing that I was telling you that makes you pull your hair out. Okay? You always have to do it. There is never be another calculation in here that you don't have to do it. Okay? Every time you do a homework problem, every time you do a quiz problem, on the final exam, you do a math problem. You get your final answer, and then you say, how many significant figures do I need? Okay, and we'll see what that means. There are some rules figuring out how many significant figures you have and figuring out whether a digit is significant, okay? Anything that's not a zero, we say is significant. So how many significant figures would you say is in 435?
435.
Three.
Three.
Oh.
So when we're dealing with sig figs here, we're dealing with, what did I do? We're dealing with decimal places. We don't really care what the number in that place is, okay? So we say 435 has 3 significant figures or 3 sig figs, okay? Any zero that falls between two digits that are significant is significant. So both 405 and 40.5 have how many sig figs? 3. Zeros to the right of a significant digit and to the right of a decimal point are significant. So how many significant figures does 5.00 have? 3. Those zeros are to the right of the 5 and to the right of the 0. So we say they are significant. Zeros to the left of the first significant digit are always not significant. 0 point something, that 0 is not significant. 0.00, none of those zeros are significant. So how many sig figs does 0.151 have? 3. How about 0.00405? 3.
Can we go back to the one before, where the zero to the right of the sig fig and to the right of the decimal point?
Right. So,
Remind me how that's 3?
so these zeros are to the right of a significant digit. A 5 is a non-zero digit, so it's significant, based on that rule.
Okay, got it.
The zeros are to the right of that, and they're to the right.
So you were just combining 2 rules?
Yes.
Got it.
Yeah.
This is a really dumb question, but what is the purpose of them choosing those to be significant? And I'm only saying this because in medicine, it's the complete opposite. You can't have any following zeros, but you have to have leading zeros.
We'll see the purpose of sig figs in the measurement lab, which I think it says the third one. What this does is this tells me how precise the instrument that you use to measurement is, okay? So this .00405 tells me that the instrument that you use to measure that can actually measure to .0000 that decimal place, okay? If you have a scale that weighs 0.1 grams and you report that to me, and you tell me that's the mass, that's not correct, right? So if you are publishing your scientific results, you're basically telling me how good of an instrument you use based on how many significant figures that you have. Okay? So in this case, these two zeros are to the right of a decimal point, but they are not to the right of a significant digit. So they are not significant. Okay? So what if I had 0.004050? How many sig figs is that?
4.
4. So these are not significant. These are, and then this 0 is to the right of these and the decimal point, so that one is also. That is 4. Okay?
So are you saying when we say we have to calculate something and it comes out to be that, we only give the sig fig?
So we'll see this, but I'll give you a sneak peek now. Say you put this into a calculator, and your calculator gives you that, okay? And based on rules, math rules that we're going to talk about, you know your answer should only have 3 sig figs. You would erase 0, and you would write that as your answer. And we'll see examples of that. and this one gets kind of fuzzy. If a number is more than 1, the 0 to the right of the last non-zero digit may or may not be significant, okay? And this is going to make sense once I write it up here. In words, it makes your head spin, okay? So if I write 100, okay? How many sig figs would you say that has? In actuality, it only has 1, okay? What makes the difference is if there is a decimal point here, okay? If there is no decimal point, the only number that is significant is the 1, okay? We say those zeros are not significant. As soon as that decimal point shows up, that is 3 significant digits.
So it's just one because there's no decimal point?
Right. And this looks very strange, you have a decimal point and then nothing past it. But that's how we do it, okay? If we want to report 100, 3 significant digits, that is the only way to do it. Like I said, it looks weird, but if we put a 0 here, how many sig figs is that? It's 4. The only way we can report 100 to 3 significant digits is that, okay?
And that's only if you have zeros.
That's only if you,
Have
yes.
zeros.
Yes, because if this was, say, 123, none of them are zeros, so by definition, they are all significant.
Okay.
Okay. So where this comes in useful, like I was talking about, if I tell you I weigh something to be 100 grams, maybe my balance, my scale only measures in hundreds of grams. Maybe it gives me 0, 100, 200, 300. And so if it's telling me 100, it could be anywhere between 50 and 150, right? But if I tell you it weighs that much, I'm telling you that my balance can weigh that small of a digit, but it actually happened to come out to be 100. So here's 400 has how many, that has how many sig figs?
1,
1. That has how many?
3.
3. I guarantee you pretty much everyone in here is going to get that wrong on a homework at some point this semester. Okay? You just have to get in the habit. Okay?
I mean, how would we, give us an example of a question that you would give us and how we incorporate?
They're covered.
Would it be a specific, like, how many sig figs are in this?
Well, that will be questions for this unit, because we're learning about sig figs.
Okay.
But for the rest of the semester, we can't forget about them. So when we do, we'll probably, and there's probably an example in here, a density problem. What's the equation for density? Mass over volume, okay? So what you're going to do is you're going to look at how many sig figs did your mass measurement have? How many sig figs did your volume measurement have? And then do the math and figure out how many sig figs your density should have. We'll see that, okay? But that is how you'll use sig figs for the rest of the semester. Every time you do math, you have to look at how many sig figs all the numbers you input had, and then you have to figure out how many sig figs your output has. Okay? So, how many sig figs does that have? How about that? 1, 2, 3, 4, 5. Are those zeros significant?
No.
Yes.
Yes.
Somebody tell me why yes.
Yes.
They're right of a decimal and to the right of significant digits. Okay? How many sig figs does that have?
4.
4. Why 4?
Because there's no sig fig and then it's on the other side of the
Right.
decimal.
Those zeros are to the right of a decimal, but they're not to the right of a non-zero digit. So these are non-significant. So it starts here, 1, 2, 3, 4. We haven't done scientific notation yet, okay? That's coming up. But when you look at sig figs in scientific notation, you ignore this. You just look at this part, okay? So how many sig figs does that have? 1. How many does that have? 1, 2, 3, 4, 5, 6, 7, 8. Okay.
So we're only, for the scientific notation one, before it's going down, we're only looking at the 9 and ignoring everything to the right?
You ignore the times 10 to something. You ignore that in sig figs.
Because if you were to actually do that, the zeros would be,
Well,
yeah, it would be like 19 zeros, and that would make
well,
160.
what you'll see, if you'd have 9 and then 19 zeros.
Yeah.
Those zeros, if there's no decimal point at the end, are non-significant.
Okay.
So if you wrote it out, there would still be 1.
Okay.
And so when you collapse that, as you'll see in the scientific notation, you would leave that as a 1. We're going to do, in all the problems this semester, you're going to do math, like I said. And then you're going to get at the end and say, how many sig figs does my answer have to have? Okay? Multiplication and division are the easy ones. You look at the numbers that you start with, and pick the one that starts with the smallest number of sig figs, and that's how many your answer has. Okay? So, if you multiply 2.06 times 4.3 in your calculator, you get that. How many sig figs should my answer have?
2.
2. Because 4.3 has 2. That one has 3. But 4.3 only has 2, and my answer cannot have any more than my lowest one that I started with. Okay? What about 6.0 divided by 3.00? What's 6 divided by 3? It's
Oh, 6 divided by
6 divided by 3 is 2. Okay? That part you can do in your head. Now we have to think about how many sig figs does our 2 have to have? 2, because it's 6.0, right? So how would you give me that answer with 2 sig figs? 2.0. Got it. You put that in your calculator, you're going to get 4.4 something. Big long thing, right? How many sig figs is your answer going to have? 1. So what would you write as the answer here? 4. Seems really strange, doesn't it? 4 times a number larger than 1 equals 4. It's like nothing ever happened, right? It's because we're assuming this 4 was from a measurement. And because we only have 1 sig fig here, that means that number is anywhere between 3.5 and 4.5. So what's the purpose of using all of these digits if our first measurement wasn't all that good? Yeah. Probably, yeah. You probably copied that off your calculator at some point. Right. Did you have a question up there?
Oh, wait, until the end.
What about 5.0 times 2.0?
250.
10.
So we know what's 5 times 2?
10.
10. How many sig figs do I need? 2. How do I do that?
That's
Point
one.
zero.
Decimal point without a 0. If I put a 0, how many sig figs does that have? 3. There you go. So,
That's what everybody's gonna do.
yeah.
On the first question, if you're using 2 sig figs, do you still have to round or anything like that?
Yeah, so that is wrong. So we're going to round, okay? So you round just like you've always rounded, okay? So what does 8.853 round to if you need 2 sig figs? 8.9, okay? So we have 8.853, and we want to round to this point. So you can kind of imagine a line there. It rounds this to here. 5.3 rounds up. So we go to 8.9. Yeah.
Now I have a question. Okay. We know we need 2 sig figs for, when multiplying 5 into 2.
Yep.
why put the decimal if it's still 2/6 big, you know what I'm saying?
If I didn't have a decimal point.
Oh, then it would be 1/6.
That's 1/6
big.
big.
Okay. Yeah, I'm gonna get that one.
I see that. Yeah, take off the back.
Luckily, the only time this really comes into play is if you do a calculation and your calculator happens to come up with a bunch of zeros at the end. Which, how often does that happen? Not all that often.
See, it bothers me because it looks stupid.
It looks really stupid.
Yeah.
It looks like it's just making a bold
Because you know,
statement
those
ten,
really tall.
Yeah.
period.
You have,
Way all our lives.
I've been doing this for, a long time. It looks stupid.
Yeah.
It looks really stupid. And I can't tell you, any time out of introductory chemistry have I ever written something like that. Okay? Okay. Addition and subtraction is ugly. Luckily, we don't do addition and subtraction all that much in here. Almost everything is multiplication and division. Okay? So addition and subtraction, you don't just look at what you start with, pick the smallest one, and go with it. You have to set it up to do it longhand. Okay? You can set it up, do it in your calculator, and then write out the number at the bottom. You don't have to actually do the math longhand. You need to be able to look at it like this. Okay? So what you do is you line all the decimal points up. See how the decimal points are lined up here? And then you let the numbers fall where they fall. Okay? And then you find the digit that is the last significant figure in a number that's the furthest to the left. In words, again, that doesn't make sense. So let's look at this. Where is the last significant digit in that number? It's the 6. It's the third decimal place, right? Where's the last significant digit in that number? The 2. It's the second decimal place. Where's the last significant digit in that? The 9. The first decimal place. So you line your decimal points up, draw a line to the right of that 9. Okay? Continue it all the way down in your answer. Do your math just like you always would, and then round from the right of that line to the left. So if you were going to tell me the answer to that, what would you write down?
4690.5.
Right. 2/6 rounds down. So it just disappears. Right? So you would say the answer is 4,690.5. Here's a hairy one. How do I do this? Line up the decimal points, right? So I have 587.362,708 and 4.36. And then, wow.
9, 2.
I'm going to have to start on the 3 by the decimal point, so I keep everything in line.
2, 9, 8, 2, 9.
Okay, point 2789. 2789. Okay, and this is plus, that's minus. Okay. So, in this case, you would want to use a calculator, okay? If you were going to do this longhand and actually do this, you would have to do that plus that, get your number, and then subtract that. In your calculator, you can do it all at once, and then we can write it down here. So I'll put my decimal point there. What does this come out to be? It's going to be a really big number, right? No, it's going to be a really small number. It's going to be a very small number. anyone has it, let me know. It's a lot of buttons to push.
It's negative.
I have
Nine, two, eight, three, three, one, eight, five, five.
Negative 9, 2,
Eight, three, three, one,
3, 1,
three, three, one,
3, 3, 1.
yes, sir.
3, 1 point.
5, 5.
5, 6.
I
Yeah, I
got
got
5,
5,
6.
6.
Yeah, it's 5, 5, 6.
Okay.
Yeah.
When you put it in your calculator, what are all the digits that it gives you on the right?
5, 6.
Two, I got a 2 at the end of my zero.
5, 5, 6,
2.
2?
I had 2, I don't know.
It's not giving you anything more than that? It should. Maybe it's cutting it off on you. Anyways, we'll see, it's not gonna matter, okay? So, there should be, well, there's probably 0, 8. Right? Because you don't do anything with that 0, 8 in your math. So, now what do I do?
Cut off
Cut it
the,
cut it.
after 5, 5.
Cut it.
Why there?
Because
Because
of the
it only has
4.36.
3 6 big,
Right.
or no?
Well, in addition subtraction, you don't go by number of sig figs, you go by the decimal point.
Okay.
Okay? So you have to draw this line. Where do I draw the line here?
After 5.
5.
3, 2.
So you're saying to draw it,
Yeah, right there,
why did you draw it there?
because
It's to the right of the very,
yeah,
Right.
it's 2 6 big to the right of the decimal, that's all.
You find the number that ends the furthest left, which in this case is the 4.36, and you draw a line at the end of that.
it's to the right of the leftmost last digit.
Exactly. Which is right there. Visually, it's easy to see. You find the one where it ends, and you draw a line. Okay? When you start putting that definition in words like he just did, then what did he just say? Okay? Yeah.
Why do our calculators give us different things, and will we be held accountable for that? Like, mine has 5 6 at the end.
To the furthest.
Did it just say 5, 6, and then nothing more?
No
Yes.
more.
It probably rounded for you.
Oh,
So, what do we do with this once we draw our line? We round it from the right of the line to the left. So,
okay, so, okay, that's right.
so 9, 2, 8, 3, 3, 1.5, 6.
Okay, you still have to round, you can't just chop it on.
Right, you have to round, you can't chop.
Too much money.
Are there any questions? Addition, subtract, yeah.
So the 3, 6, the reason why we cut it off after the 6 was because that was the number with the smallest amount of sig figs.
It was the one number with the least number of decimal places.
But yeah, that's
Yeah,
kind of
so,
like,
yeah, what if you had, instead of this number, instead of 4.36, you say you had 0.0009, okay? That only has one sig fig, right? But that doesn't matter to us in addition and subtraction. Now, where would we draw the line?
To the right of the 9.
Right, in this case, these two end in the same place. And those are they end furthest left. So we draw a line here.
so then it would be blah, 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 5, 5, 6, 2.
Right, so 6, 2, and then 0, 8 rounds down,
Gotcha.
right?
Uh-huh. Okay.
So everyone see that, because if you don't, and you don't figure it out at some point, you're gonna get this wrong for the rest of the semester.
The only thing I'm worried about is the calculator rounding it for us, and then we're gonna round from the calculator, we're gonna get it wrong.
Well, with the
I think what happened here is your numbers were so big, it had to round to fit on your screen. You normally won't be dealing with these large numbers. These large numbers were for an example to show you. It doesn't matter how many you have here, it doesn't matter how many far this one goes over. This one could extend all the way down here. It doesn't matter, you're still gonna round here, because you're 4.36 in here. Okay? Did everyone who did it, if you calculate, didn't round get 556 something?
It's got 5, 6.
Okay, so yours rounded. I know my slide says 0.55. Okay, so I'm guessing. What I'm guessing, more likely than chopping it, I typed into my calculator wrong. Is more likely. So everyone make a note that that should be 0.56, not 0.55. If you leave it as 0.55, tomorrow when you go back to look, you're not going to remember that I told you it was wrong. You're not going to be able to figure out why it's 0.55, because that doesn't make any sense. Okay. Last thing we'll talk about before break, scientific notation. We saw that. How many of you have used scientific notation before? So about half, it looks like. Okay. So scientific notation in math speak is a C, a constant, times 10 to the n. An n can be an integer. What is an integer?
Any number? It could be less than zero.
A number without a decimal. It's a whole number. Okay? It can be positive, it can be negative. But you can't have 10 to the negative 1.1. You can have 10 to the negative 1, you can have 10 to the 1. You can't have 10 to the negative 1.1, you can't have 10 to the 5.8, anything like that. The exponent there has to be a whole number, okay? That C is always a number between 1 and 10, always, okay? If it's not, you did your scientific notation wrong. To get C, you move the decimal point to the right of the first non-zero digit in the number. Again, in words, it sounds horrible. Okay? Let me erase this. So let's say I have 109783, and I want to put the decimal point. First of all, where is the decimal point now?
Behind the 3.
It's right here, right? It's assumed. We don't write it in this case. That 3 is significant whether I have the decimal point or not. So I don't need the decimal point. You can fall back to what you've been doing since first grade and not write it. Okay? So if I want to move the decimal point to the right of the first non-zero digit, where is that?
To the right of the first non-zero digit, so that would be after 1.
After the 1. So I put it there. Is that between 1 and 10?
Yeah.
Yes. Right? If I put it here, is that between 1 and 10? No. What if I put it here?
It's greater than 10.
Greater than 10. The only place I can put it between 1 and, so it's between 1 and 10 is there. Okay? Simply, it goes after the first digit. Period. Okay?
Is that unintended?
The not intended, but very serendipitous. Okay. So the n, our exponent, our integer, is equal to how many places we moved. If we go to the left, then our n is positive. If we go to the right, it's negative, okay? How many places did you move here?
5.
1, 2, 3, 4, 5. So where is our end?
To the field.
Right, 10 to the 5th. So if I want to write that number in scientific notation, how do I do it?
1
Times 10
times
to the 5th.
10 to the 5th.
7, 8, 3. We can't lose our sig figs. Okay? In this case, putting in scientific notation actually is just going to make more work for us, right? We wrote the same number of digits and then times 10 to the 5th. In a lot of cases, when you have zeros at the beginning or the end, it will save you a lot of effort, okay? So what if I have 0.009? What is that in scientific notation?
Times 10 to the third power.
Right. So I have 9. How many sig figs do I have to have when I get to scientific notation?
3.
So 1. That 9 is significant. These zeros are not. Okay? So I can just, when I get to scientific notation, I can just put 9 times 10 to the
To the middle.
negative 3. So I started here, I'm going 1, 2, 3, and I went to the right, so it's negative. Okay? So, if I'm going to put that in the scientific notation, am I moving the decimal point to the left or the right?
Left.
Left. So, it's times 10 to the third. How about that one? Left or right? Right. Times 10 to the negative 1, 2, 3, 4, 5, 6. Okay? How about that one? Left or right?
Right.
Left. At the moment it's here. We're going to move it down here. If I want to write that out in scientific notation, how do I write it?
3.245 times 2 to the
3.245 times 10 to the 9th. These zeros are not significant. If there was a decimal point there, they would be, but they're not. So when I go to scientific notation, I can ignore them. Okay? If there was a decimal point there, I would have to put 0, 0, 0, 0, 0, 0 times 10 to the 9th. Okay? I don't have to though, because they're not significant. Does everyone get this? Anyone want to do the last 3?
No.
Okay.
No, I mean,
Okay. So, on this one, are you going to move decimal point to the left or the right?
you have to move it to the right.
Do you see that?
Yeah.
Okay.
Okay, what about the whole numbers kind of,
The 88 or,
no, the one
Okay.
at the top? So I would be moving the decimal to the left, and
Right.
it would be 3.245 times 10 to the negative 4.
you're talking this one?
The first,
So you have 3, 2, 4, 5. You're going from here to here, right? So it's 1, 2, 3. So you have 3.245
okay.
times 10 to the positive 3.
Okay.
You went to the left, so it's positive. We moved 3 places, so it's 3. Does it make sense? We can talk about it right.
Okay.
Okay.
What about the last one?
Yeah, the last one already had the decimal, so what would the scientific notation be?
So, if you really, really wanted to put, I personally would leave it like that, okay? If you wanted to put times 10 to the something, how could you do that?
End of the 1.
Well, if you moved it to the left, now we're not between 1 and 10, so we can't move it.
That'd be 10 times 10 to the 0.
Times 10 to the 0. If you take it, I don't know what math class that's in, anything to the 0 is 1. If you multiply by 1, nothing changes, right? So you can go 2.45 times 10 to the 0. You would never do that. There's no reason to do that. Okay? So in that case, you could put 2.45, or if you really wanted, you could write that out. Okay? All of your calculators are going to do this differently. Some of them, you do a number, and then there's an E. It's a little capital E. It is not lowercase e. That is very, very, very different. Okay? Some, it'll be EE, some will be EXP. You're gonna have to figure it out. If during break, which we're gonna take right now, you wanna bring it up and we can look at it together, you can figure it out. The other way you can do it is you can put in a number times 10 to the 5th. But if you do that, make sure you get your order of operation correct. If you do this, and you do multiple things, addition, subtraction, all kinds of stuff, and you don't put parentheses in, you're gonna get a horrible answer at the end, okay? So let's take a 15-minute break.